Okay, so this is part three of, of my review. I apologize. I'm not great early in the morning doing these things. And I just at the very end of the second of these three little reviews, ignore the part about digestive. I flipped on to a different exam and I have no idea how or why I did that. So excuse me. We have to do respiratory and blood vessels, and I'm doing that right now. So thanks again. When it comes to respiratory, okay, there's so many different factors, but generally, uh, air flows well. And what happens, other than chronic respiratory diseases or acute respiratory disease? So if you have an asthmatic attack, obviously it doesn't. The tiny bronchioles constrict. But under normal circumstances, there's not a lot of resistance. The channels stay open because the cartilages in the non-diseased or non-infected individual. Whatever resistance there is statistically is surprisingly not at the bronchiolar or alveolar level, but in medium-sized bronchi. Remember, it's a function of the overall diameter, which includes not a, one this diameter of the vessels of that category, but all of the diameters. So when it starts to branch, even though the diameters get smaller, the surface area gets larger, and that's how they do the calculation. And so that's really a significant part of the respiratory aspect of those types of things that are there. And I think that's one of the things you have to be at least wary of. The role of surfactant. What it is, it's a wetting agent. And so wetting agents basically don't allow structures to adhere to one another. And so, as long as that's there, because they're constantly opening and closing the alveoli, they don't adhere to one another very, very well. We start producing it in during gestation and it's produced throughout your lifetime, and we're able to now make it, which has eliminated a lot of the not eliminated is the wrong term, but limited a lot of the problems associated with premature infants and even improving some cases of respiratory disease of the newborn, which is caused by a virus that's rearing its ugly head in adults much more now, which is respiratory syncytial virus or RSV. Okay, carbon dioxide and oxygen are so easy to exchange because you have a shared basement membrane alongside simple squamous cells. It goes directly through these membranes because it's fat compatible. It's classic simple diffusion. Okay, the distinction is the oxygen relies on concentration gradient. Carbon dioxide is much more soluble, even though it has a concentration gradient to drive it. It's just very, very small comparatively. And basically, the notion that in respiration, the oxygen certainly travels along the heme groups, but the carbon dioxide is divided into three areas. A small percentage travels dissolved in the bloodstream, as gases do. There's a certain amount, maybe 20%, that rides on the globe, and the rest of it combines with water and forms carbonic acid to permit that wonderful carbonic acid buffer system that's there. And when it comes to respiration, our primary stimulus is carbon dioxide concentration, then pH, then oxygen concentration. The CO2 is the most important, and the CO2, because of the carbonic acid buffer and its relationship in producing alterations in pH or even stabilizing them, but in circumstances it causes the pH to also be impacted. That's an important thing. So as we lower pH and accumulate acidity, that's the secondary force. And if we get to the point where it's oxygen concentration, you got trouble to be there. We have obstructive and restrictive disorders. Obstructives are blockages, they're in the conducting division. Restrictive are in the respiratory division. They involve the exchange of oxygen and carbon dioxide. We measure those with those pulmonary function studies we did in the lab, which I think are very interesting. We have all those volumes, volume, the amount you bring in and out in a typical breath you're not even thinking about, the large inspiratory reserve, the little more limited expiratory, not inconsiderable, but a little more expiratory reserve. And if you add that with the tidal volume, those two reserves, we have the vital capacity. The total lung capacity brings in residual spaces. Some of it's dead space, some of it's spaces that are not effectively being used, if you want to think of it that way. So when we talk about FEV1, we're looking at measuring an obstructive disorder. You should be able to get approximately 80% in a second. That's with forced expiratory volume at 1 second. Okay. If you can't do that, then it implies obstructive. Restrictive disorders have to do with vital capacity diminished based on what the expected value is, because it you have less ability for the exchange. It's about the exchange. That's damage within the alveolar level. You have different effects that play a role. Bohr and Haldane, you should be familiar with what they do. Know the distinction between the one that impacts the unloading of oxygen gas and the one that impacts the unloading of carbon dioxide. And know the way that breathing is basically only active in its inspiratory role, which involves the diaphragm and the external intercostals. The internal costals, abdominal muscles, accessory muscles, we only lose when we have difficulty breathing for whatever reason, or we're forcibly breathing in or breathing out. We have to understand the oxygen saturation curve. It's so important. It's not a linear relationship. And understand and remember the definition of emphysema, trapped air. As we finish up with this unit, we go back and look more at blood vessel dynamics. And I always like to use the two together. The key issue is what blood pressure is. The diastolic is the critical number. Systolic varies. If systolic is consistently high, then you have to understand, and then there's a problem. Then maybe the compliance or the distensibility of the blood vessels is an issue. Maybe there is some disease entity. Maybe it's a long-term problem. All those types. But when we get agitated or excited, that number goes up and down relatively quickly. That bottom line number, the diastolic, the resting tension, is a key measure because it gives you an idea of peripheral resistance. And that's what we look at. For your ages, 80s, for my age, maybe 85 to 90, even up to 90 as you get older. But for a young person to have consistently be at 90 or above, big trouble. I mean, now there's just too much tension in that system. And what happens is that that's damaging over time to blood vessels. That's damaging to the heart over time. It causes it to enlarge, etc. If you look at the charts that are there, there's always a misconception. Okay, when we look at blood flow, the one area that remains constant, whether you're active or inactive, is blood flow to your brain. It doesn't change dramatically with things like exercise or lack thereof. It's always about the same. And I think that was misstated in the PowerPoint, and I certainly am making an effort to correct it. The big players with respiratory controls are the aortic and carotid sinuses. They really have an impact on those. They really play a role both with, and what do they do is they adjust it by heart rate and force of contraction. The the aortic and carotid bodies are chemical sensors that kick in afterwards. They're sort of secondary measures. We use pressure first, and then to adjust heart rate and force of contraction. And then the respiratory system becomes involved when we start to look at CO2 and pH and PO2. I think you should be aware of that. Blood's interesting because we always think we learn all the names of the arteries, but it's mostly in the veins. It's almost a 2 to 1. It's more than a 2 to 1 relation. 2/3 of blood in veins, maybe 15 or 20% in your arteries at one time. Venous return is underestimated, but of great importance. It's facilitated anatomically by valves and muscular activity. We want to look at arterial pressure. The big number, and we did a lot of this in kidney as well, is the MAP, mean arterial pressure. Look at the diastolic, look at the pulse pressure, which is this difference between systolic and diastolic, divide by 3, and add it to the diastolic. So 120/80 effectively makes it 93.3. Don't forget the role of angiotensin converting enzyme and that renin to angiotensin 1 to angiotensin 2 pathway. That's also important. All the 4 activities of angiotensin: tensing blood pressures, inducing thirst, releasing antidiuretic hormone, triggering the aldosterone, which is probably the most important, what aldosterone does with sodium and water following it. And so all of those are really significant. Don't forget the nugget that we looked at both in cardiac and in blood pressure, that were all those elastic or conductive arteries. The fact that they create that rebound effect that prolongs the force of blood pressure without an undue amount of turbulence, particularly at the closure of the aortic and semilunar valves. Okay, and so and interestingly enough, and different than respiratory, it's when we get to the tiny blood vessels where the smooth muscle can overcome and constrict. Is where we have most of our controls. That's the arterial level. And I think that basically covers everything in a long winded, three pronged pattern. Thank you very much. And I'll send all these to you.